Runge-Kutta method. So in the previous one, right, so I have discussed Runge's method, a little improvement than that. So this is Runge-Kutta's method, right? So this is also called as Runge-Kutta's fourth order method also, right? So here actually the way we are doing in finding out the solution of the differential equation for any random curve like this, if you know one value, that is at x0, the function value is y0, and we are trying to solve the differential equation of the form dy by dx is equal to f of x comma y. So this is the function actually for which we wanted to solve the differential equation. Now in this case, so at this location, we tried drawing a tangent, and this is the tangent, and then this is a horizontal line, and here we wanted to find out the value of y. So which is nothing but the solution of the differential equation provided if you are able to find out the value at this location, right? For that, the methodology what we have adapted in case of Runge's method is we divided this into two equal parts, and this is h by 2 and this is h by 2. So this is h by 2 and this is h. So this is divided into two equal parts, and then the methodology what we have adapted there is integral dy. So this actually brings out to be f of x comma y dx, and then from x0 to x0 plus h, and this will be from y0 to y0 plus k. So which essentially means that if this is y0, then actually this is the value of k which you wanted to find it out. So this is the value of k. So if you substitute here, so dy will be y, and upper limit is y0 plus k, and the lower limit is y0, and then these two will cancel out, and this will be equal to k is equal to integral x0 to x0 plus h and f of x comma y dx. So this is the integral actually which we wanted to find it out. So from this derivation, what we can understand here it is, if you are able to find out this integral value, you will be able to know the increment value of k, right? So this integral value we will be solving with the help of Simpson's one-third rule. So in case of Simpson's one-third rule, so for a function of this particular format, and if you want to find out the area between this one and this one, taking this as the y0 and this as the y1 and this as the y2, and then so this is x0 and this is x0 plus h, and this is x0 plus 2h. Yeah. So this one actually, when we tried solving this integration, so in case of Simpson's one-third rule, what we have solved is the function integral value, integral, so x0 to xn, so this is f of x dx. So this value we found with the help of h by 3 times of y0 plus 4 times of y odd sigma plus 2 times of y even sigma. So this is the formula for Simpson's one-third rule. Now here what we are trying to do, in case actually if we have only three parts, that is x0 and x0 plus h by 2 and x0 plus h. Now if there are only three, then actually this Simpson's one-third rule will become h by 3 times of y0 plus 4 times of y1 plus y2. So this is the Simpson's one-third rule in case if you have only three different numbers or three different points, right? Now this rule actually, if you wanted to apply it here, so rather than h actually this was divided into h by 2, not as a h. So because actually we have made x0 to x0 plus h in two different equal parts, so h becomes h by 2. Then actually to solve this integration, it will be h by 2 times of 3 getting multiplied by this y0 plus 4 times of y1 plus y2. So this is the integral value. So this will represent the k value. So h by 6 times of y0 plus 4 times of y1 plus y2. So this is the integral value. So that's why actually in case of Runge's method, so this is going to be h by 6 or 1 by 6 times of h into y naught and 4 times of h into y1 plus 2 h into y2. So this is how actually you are going to represent the value of the integral with the help of Simpson's one-third rule. So this is going to be represented in terms of the k. So this is actually Range's method. Now here actually in case of Range's method, what we are trying to do here it is, this value is treated as if like this value. So this is actually ideally, this is y naught plus. So this is this height actually. So this height we are treating rather than this height. That means this value whatever is there, right? So you are taking this as the ys. So I call this as s, and then here we take as ys. Ideally we should have considered this value because we don't know the solution of the differential equation yet. So that's why actually we will be able to find out this value with the help of the slope at this point, and then this actually we treat or we consider as if like this as ys in case of finding out the Simpson's one-third rule. So this y1 role is getting played by ys, not the ideal value or the ordinate value of the function. So this value will be crucial for us. So this one actually we are going to calculate, this is the angle theta. So the slope at this point, so dy by dx at x0 and y0 is the slope. So f of x0 comma y0 is the slope at this point, and this will be, so this is h by 2, and this height you will be able to find out h by 2 times of tan theta. H by 2 times of tan theta is f of x0 y0. So h by 2 times of f of x0 y0, this value will be this height. So this height actually we can calculate. If we add y0 to that one, so this one actually the value of the function from this point, let us say a to s. So this is going to be as. Now here actually when we are calculating it, so what we are doing is we do consider the same angle theta, and then this length is h, and this height you will be able to find out, let us say I call this as q. Then this q value or from here to here you can calculate till this point, this is y0, and this point is actually so h times of tan theta. So this is h times of f of x0 y0. So this is the function value at this particular location. Now in Range's method there is a little improvement than this calculation. Ideally actually we wanted to find out this value. For that actually what we have done is, once you find this value, this actually we call this as k dash, and this k dash value we will be making use in identifying the slope of this particular function at this location as if like in this particular format. So in the next iteration actually what we are trying to do is, you consider this slope for calculating the value which is better than this. So this actually a little closer if you consider this slope at this particular point. So this value we will be calculating it now from here to here. Got it? So this is the improvement in case of Range's method. Now in Range-Kuttas method, the difference is rather than the improved slope here, we do consider the improved slope at this particular point. So we do consider the improved slope at this particular point, and then we have an existing slope already based on this understanding, and then a little improved slope you will be able to find it out here. And then rather than improving the slope at this point, we do improve here itself, and then actually we take normal slope plus the improved slope two times together rather than the 4 times one slope here. So here actually what we are trying to do is, for the value at y0 you are giving single weightage, and for the value at the last point you are again giving the single weight, but the value at the midpoint actually we are giving 4 times the weight. So as you are giving the 4 times the weight, if you are able to make a little improvement in this, then actually there will be improvement of 4 times. So rather than improving here actually we have improved it. So that is Range-Kuttas method. Got it? That is the little difference between these two. So this is going to be divided into 2 different parts. So 2 times of k2 and 2 times of k3, and this is k4 like that. So these 2 times of k2, k3 are, so this k is nothing but h times of y0. H times of y0 is nothing but the k. So this actually ideally rather than y naught, actually here the function value is f of x naught comma y naught. So this is going to be h, so 1 by 6 times of, so I'll write it here, k is equal to 1 by 6 times of h times of f of x naught y naught plus 4 times h times of, so f of x naught plus h by 2 comma y naught plus k1 by 2. And then plus h times of f of x naught plus h comma y naught plus k. So this is the value actually which we are going to calculate in case of Range's method. Now the improvement of this is actually we will be improving here itself. First you note down this, then actually we will write the improvement part of it. So k1 is actually h times of f of x naught. So this is what is called as the k1. So I have given all the formulas yesterday. So I'll just write it. First you note down this, whatever is visible, I'll write this part again. Then so in Range's method, right, what we are trying to do is, first actually we calculate k1. So k1 is nothing but h times of f of x naught y naught. So this is k1. Now, and then k2. K2 is actually h times of f of x naught plus h by 2 comma y naught plus this k1 by 2. So this is k2. And then actually rather than calculating k3, we do consider k dash. So this k dash is h times of f of x naught plus h and y naught plus k1. So this is actually y naught plus k1, this is k dash. Now we will use this value to increase the better accuracy at this particular location. Now actually we have calculated this value by considering y naught plus k1 here. So now actually the slope is upgraded, and then k3 you can calculate as h times of f of x naught plus h comma y naught plus k dash. So this is the improved value. Now for these values, so k1, k2 and k3, we will be writing the k value which is the weighted average of all these things. So this is k1 plus 4 times of k2 plus k3. So this is the k value, and the y new value is nothing but y old value plus k. So this way you will be able to find out the value of the y at x is equal to x naught plus h. Got it? So this is Range's method. Now here actually what we have done here it is, so k2 is actually h times of f of x naught plus h by 2, y naught plus k1 by 2 is k2. Now actually rather than k dash, here itself actually we will use this k2 value to improve this value here. So this one actually now k3 equal to, we call this as k3 h times of f of, I'll write it here, k3 equal to h times of f of x naught plus h by 2 comma y naught plus k2 by 2. So this is the improvement in case of Range-Kuta's method. So h times getting multiplied by, so this k2 usage is the better thing. Now once you calculate k3 and then actually, so k4 actually we can calculate, k4 is equal to h times of f of x naught plus h comma y naught plus k1. So this is only k1 only, right? And then actually, with the help of Simpson's one-third rule, Runge-Kuttas method, so this the weighted average of all these values case. So this k is equal to h by 6 times of k1 plus 2k2 plus 2k3 plus k4. So this is Runge-Kuttas method. Got it? Understood? So being this actually given 4 times the weight, so we have divided into 2 different parts, one before improvement and another after improvement. So this is actually before improvement. So this is as usual, by considering this slope actually we have calculated this value. And then once you got this value, we tried drawing a tangent parallel to this curve at this particular point. So this is the tangent actually which was written here or which was drawn here by considering this value of x and this value of y. So earlier actually, so this value we have considered for y. Now actually we have considered this value for calculating a better value, which you can get almost closer here. So that was given better weight. Got it? So this is Runge-Kuttas method. Which one? So this K4, right? Yeah, K4 is actually x naught plus h and y naught plus k. K1. This is K1 only. So the same weight of this one is given. Here actually this improvement is not there in case of Runge-Kuttas method. That was done here. In Runge's method, rather than here, we have done here. This change. Got it? Done? So now you can note down one problem on Runge-Kuttas method. K1 and K2 in figure. This is x naught. This is x naught plus h by 2. This is x naught plus h. Here actually there is a tangent drawn at this location. And this is a horizontal line. So here actually K1 actually we have defined as h times of f of x naught comma y naught. So f of x naught comma y naught is nothing but tan theta. H tan theta is the K1 value. So h tan theta is the K1 value. So h is actually this length and then tan theta is this height. So this is K1. Got it? And then the next one is h times of f of x naught plus h by 2 comma y naught plus K1 by 2. So here actually the point is x naught plus h by 2 and y naught plus K1 by 2. So that location is K1 by 2. So for this actually half of that actually it was considered here for this one. So somewhere here actually you are going to get it. Now this value and this value are considered for the purpose of tan theta at the location of x naught plus h by 2 come y naught plus K1 by 2. And then here actually this is as if like drawing a tangent to this curve at this location by taking these values at this location. So this is how actually you will be drawing. Now this tan theta value we have considered it. Got it? So this tan theta value, so these are actually some random constants actually. We cannot represent straight away in the diagram. So K1 you can represent it. But for K2, so this is h times of slope at that particular point. Now h is as if like if you consider from here, this is as if like somewhere here. and then draw a value like this, and then this is going to touch here, and this height actually we will be considering, and then project that value here. So this is how actually you can interpret it. So these are actually some constants actually that are used in case of calculating the Simpson's one-third rule. Got it, Pankaj? So note down on problem. Apply Runge-Kuttas fourth order method to find an approximate value for y. Apply Runge-Kuttas fourth order method to calculate an approximate value of y when x equal to 0.2, given that when x equal to 0.2, given that dy by dx is equal to x plus y, and y equal to 1 when x equal to 0. So this is the value, this is the problem statement. Now actually when we are using the Runge-Kuttas method, so we will be identifying, let us consider, so this actually we need to calculate the function value at 0.2. So at 0.2 actually we should be considering. Now actually let h equal to 0.2. Then the k1 value is h times of f of x naught comma y naught. So this is 0.2 times of f of x naught comma y naught. So x plus y at the point 0 comma 1. So this is 0.2 times of 0 plus 1. This is going to be 0.2. This is the k1 value. Now k2 value is h times of f of x naught plus h by 2 comma y naught plus k1 by 2. So this is k2 value. So h is 0.2, and then for x plus y, so this is x naught plus h by 2. So h by 2 is, so 0 plus 0.2 by 2 plus y naught is 1 plus k1 is 0.2 by 2. So this is going to be 0.2 times of 0.1 plus 1.1. So 1.2. So this is 0.24. Okay. So now k3 is h times of f of x naught plus h by 2 comma y naught plus k2 by 2. So h is 0.2 and x naught is 0 and h by 2. This is 0.2 by 2 plus y naught plus k2 by 2. So y naught is 1 plus k2 is 0.24 and by 2. So this value is coming out to be 0.2 times of, so this is 0.1 and this is 0.12. So 0.1 plus 0.12. 0.1 plus 1.12, 0.22, 1.22. So 1.22 is 2.44. So 0.244. So this is the value of K3. Now K4 is h times of f of x naught plus h and y naught plus k1. And this value is 0.2 times of x naught is 0 plus 0.2 plus y naught is 1 plus k1 is 0.2. So this value is 0.2 times of 1.2 plus 0.2. So this is 1.4. 1.4, 2.8, 0.28. So this is the value of K3, which is 0.28. I'll write it here. Now, K value is 1 by 6 times of K1 plus 2K2 plus 2K3 plus K4. So this is the value of the answer. So this is 1 by 6 times of, and K1 is 0.2 and 2 times of K2. So K2 is 0.24. So this is 0.48 plus 2 times of K3. So this is 0.488 plus K4 is 0.28. So this is going to be K equal to, so this is 0.6. 1.4568 by 6. So this value is 0.2468. So this is 0.2468. So Y new is equal to Y old plus K. So this is 1.2468 is the Y new value with the help of Runge-Kuttas method. Got it? I think for the same problem we have got 1.2426 in case of Runge's method. Now actually for this problem we have got 1.2428. So a little difference is there, 0.2426 and 2468. Got it? So this is how actually you can make use of this Runge-Kuttas method in case of numerical integration, numerical solution of the differential equations. Got it? Yeah. So this is actually the most popular method. So being actually this is a better accurate value, at the same time easy to calculate. So straight away, without even worrying about the differential equation, if it is of the form f dy by dx is equal to f of x comma y, then straight away calculate this k1, k2, k3 values, k4 values, and then actually calculate 1 by 6 of all these things, and then actually you can straight away say that the value of the increment or the next y value is going to be the sum of y naught plus the k value. Got it? Yeah. So this is about the Runge-Kuttas method. Now, so the computer programming, I left with actually the flow charts and algorithms. So I will complete that. Now, here actually the concept here it is, when we are, so this numerical methods is actually just to make use of the computers to solve our mathematical problems with the help of numbers, right? So this is the final summary of this entire topic. In that, so flowcharts and algorithms actually, so a mathematician knows that actually how to solve a particular problem, but a computer engineer may not be. So for that actually, we have to have a better communication between the computer programmer and the mathematician. Now for that actually, there are two different popular methods actually which we are going to use in case of computer science. That is the algorithms and the flowcharts to express the methodology how to solve a particular problem, so that actually the computer programmer will use these steps as it is, and then actually he will implement with the help of computer programming. Got it? So this methodology of communication is called the flowchart or algorithm. So here actually an algorithm is nothing but a sequence of steps describing the solution. Solution of the problem. So that the computer engineer, the computer programmer will make use those steps to implement the solution. So this is an algorithm, and a flowchart is exactly the same thing but represented with the help of symbols. A flowchart is a diagrammatic representation of the solution. A diagrammatic representation of the solution conveying specific meaning for each symbol that was used. So this is a flowchart. So flowchart actually will represent the same thing, but actually in a systematic diagrammatic manner, so that actually the programmer can easily understand just a glance. Here actually he needs to study all the steps. Now all the steps actually more or less actually in case of algorithms and flowcharts, right? So we will be repeatedly doing many steps. So rather than every time actually you are writing the same step again and again, if you put it in a diagrammatic manner, that will be far easy to understand for the programmer. So there are certain symbols, not many, I think 4 or 5 symbols are there. So those symbols are, so this is start or stop of the program. So when you are representing a start or stop of the program, so you will be using a parallel line and with a curved completion here. So this is start or end of the program. And then diamond shape is used for decision making. And a rectangle this is used for the computer process. Process meaning if you wanted to implement a specific step, that you can write it in this rectangle. And a parallelogram is used for the input or output. Right? So these are the standard symbols actually that are going to be used to implement a flowchart. Got it? So this is actually flowcharts and algorithms. Now let us take one problem. So that problem, let us say bisection method, actually we take it and then actually try to write all the steps and try to represent it with the help of flowchart, so that you will get a fair understanding on what we are going to do in case of flowcharts and algorithms. Got it? So is it noted? Okay. Now in case of bisection method, what we are trying to do is, suppose if you want to identify the solution at this location, we will be identifying 2 different points first. So one point has to be here, let us say we call this as x1, and then another point has to be here, let us say this has to be x2. So we'll write that steps first. So assume an initial value for x1 and then calculate the value of the function in the second step. Assume another value or another initial value for x2 and then calculate the function value f of x2. So here f of x1. In the third step, check if the product f of x1 into f of x2 is less than 0. The fourth step, if the value of the product in step 3 is not less than 0, then go to step 2. So here actually if the condition fails, then actually what we need to do, we have to check for another value of x2. So that means you go back to step 2 and assume one more value for x2 and then try to calculate the product again, and then if it is still the same, if it is not less than or equal to 0, that means if it is a positive number, then x1 and x2 values, suppose x1 is here and x2 is here, then actually the product of the function value is negative into negative is going to be a positive value. And even here actually if x1 is here and x2 is here, the product of positive into positive is again a positive value. Then actually you cannot find a solution between this value and this value or this value and this value. So that was a wrong thing. So hence actually what we need to do, if the product actually, if it is not less than or equal to 0, that means if one value is here and one value is here, this is x1 and this is x2, then obviously f of x1 and f of x2 will definitely be less than 0. Hence you can say that there is a solution that lies in between these two as long as this curve is continuous, right? Now here we have to go to step 2 back. So in the fifth step, if the product is less than 0, then find x3 is equal to x1 plus x2 by 2. So this value actually we need to be finding out. Then again in step 6 actually find the functional value of f of x3 and check the products to f of x1 into f of x3 less than or less than 0 or f of x1 x2 into x3 less than 0. Now in this case actually definitely there will only be one value which will give this result of negative value. So if the product with the f of x1 is negative, then obviously this is going to be positive. If this is negative, then this is going to be positive. So we need to pick up a value which is giving a negative result for the product of f of x3 into f of x1 or x2. So that value we need to be picking up, and then actually you can calculate the next step by reassigning the same process. So you note down this, and then we are going to erase it and then write the next steps. Done. So find this one. So now actually, if f of x1 into f of x3 is less than 0, then repeat or go to step 5 again. With x1 and x3, or if f of x2 into x3 is less than 0, then go to step 5 again, with x2 and x3. And then, so here actually, once the step 6 gets over, and then actually we need to, so I think so this is the 8th step, and in the 7th step we need to do store the value of the function f of x3, and then check this value against previous value. For the error, right? So here actually, as and when we are calculating this functional value, and then in the first step actually we store that number. And then in the next step actually, when we calculate x3, f of x3 again, if the error is actually, so we calculate actually f of x3 old minus f of x3 new is less than or equal to the error. So we check this, and then actually we will proceed, or whether to go for step 5 or not, we will decide this. Based on this actually we will go to step 7, 8. Got it? So like this actually this process will continue. So every time actually it puts a value for x3 and then check the condition that f of x into f of x3 is less than or equal to less than 0. If it is less than 0, then actually we take that value of x3 and then check for the previous value. So this is actually, if it is the less than the error, so this error actually will decide whether to continue or not. If this condition is satisfied, then you stop it. Otherwise, go to step 5 again. That is going to be decided in step 8. Got it? Understood? So this is how actually you can write the flow chart, so that actually you can convey to the programmer, he can implement based on these steps. Got it? This is expected and he has to code according to this one. Now same thing actually we can do with the help of a flow chart. Flow chart is far easier than writing these steps. So in case of flowchart, what we are going to do is, first actually we start the program. Now here actually generate two random numbers. And then calculate f of x1 and f of x2. And then you need to check if the product f of x1 into f of x2 is less than 0. So we need to check this condition. So here actually there are two different cases after checking this. So this value may be true or may be false. Suppose if it is false, then what we need to do? Again actually generate the random number and then this will be given here. Again actually it will check for f of x1 and f of x2. So with the new value of the random number which was generated here. So here actually another case is if it is true, that means actually this condition is true. If it is condition is true, then what we need to do is we need to calculate the x3 value as x1 plus x2 by 2. So this value actually we need to be calculating it. Once you calculate this, then find the value of f of x3 also here itself. So once you calculate the f of x3 also, then you need to check for this condition, that is so here actually, so in the generate random numbers, here actually we can generate the error also. Sorry, set the error. Error limit. And then one more thing actually what you can do is, so set the error and initialize f of x3 to 0 first. So when you initialize to f of x3, then actually here we can check that if this condition is true, then you can check that f of x3 new minus f of x3 old, and this value is less than or equal to error. So error was initialized and f of x3 initially, this is f of x3 old is 0, and then now we have calculated f of x3 value like this. So once you calculate f of x3 value, then actually you can give that as the input to this one, and then we'll check for this error, right? So this actually, this is a condition here. So this condition actually we need to be checking it, and again you can get two different results. So maybe true and maybe false. So this is true and this is false. So if this condition fails, then what we need to do? We need to repeat the steps. So that is generate, so use this value and then calculate the function value here. So you need to give this, and then again actually it continues, come back to here and it will calculate the f of x3, check for the error, and then if it fails, again come back, and then again calculate this value and check for this, and it continues. If the condition is true, then actually the error limit is reached, then actually you can stop the program. Got it? So this is how actually you can write the program, or you can write the flowchart for any kind of methodology, whatever you are going to adapt it. Maybe a regular fallacy method, maybe a bisection method, or Newton-Raphson method, whatever it may be. So exact the mathematical procedure, whatever we are going to do, if you write in words, then we call that as a algorithm. If you put it in a diagram with this kind of symbols, we call that as a flowchart. So if you know the solution, then actually writing this is up to you. How do you want to write it? So every programmer might implement in a different method, but the steps are more or less the same. Right? So any questions on this flowchart and algorithms? Any questions? Okay, so this is the last class for this numerical methods. I hope I have covered every part of it. So without leaving anything, so I covered 100% of it. So this is the last class for numerical methods. And then, so in the next class actually, I'm going to start with ordinary differential equations on Wednesday. So till then, no classes. Yeah. Got it? Yeah, that's all for today. Yeah, thank you. Good night.